Before humanity ever reaches another star, it faces a problem far greater than rockets, fuel, or technology. The universe is simply too vast. The nearest star beyond our Sun is trillions of miles away. Even the fastest spacecraft ever built would take tens of thousands of years to get there. Every destination beyond our solar system lies across distances so enormous that human lifetimes become almost meaningless. Tonight, this journey explores the real reason humanity may never travel between the stars. Not because of a lack of ambition, not because of a lack of intelligence, but because the laws of physics themselves may stand in the way. If fascinating journeys through space science and the mysteries of the universe help make evenings a little more relaxing, take a moment to like this video, subscribe to Cosmic Bedtime Stories, and join future adventures among the stars. Now, as the universe slowly unfolds, the true scale of interstellar space begins to emerge. Space between stars forms the outermost context in which the idea of interstellar travel is usually imagined. Yet this region is defined less by objects and more by absence. The nearest star system beyond the Sun sits at a distance of several trillion kilometers, and even this closest neighbor represents a scale so large that everyday experience offers no intuitive comparison. In this outer region, matter is spread so thinly that a single cubic kilometer may contain only a few stray atoms, mostly hydrogen, drifting with no coherent structure. The emptiness is not uniform in its simplicity. It contains faint clouds of gas and dust, but these structures are scattered across vast gaps where nothing accumulates into solid form. The perception of space as empty becomes more accurate here than anywhere within planetary systems, and this emptiness becomes the first fundamental barrier to travel. Within this region, distance is not merely a measure of separation, but a physical condition that shapes every interaction. Light itself, which travels faster than any known object, takes years to cross even the smallest interstellar gaps. The nearest star beyond the Sun is so far away that its light requires more than 4 years to reach Earth, and this delay defines a basic limit on how information and influence propagate. Any attempt at travel must exist within the same constraint where even the fastest possible motion requires long durations to bridge gaps that appear static and unchanging on human timescales. The scale expands further when considering the broader structure of the galaxy, where stars are separated by distances that multiply this baseline by many times. In this outer environment, navigation becomes a concept tied entirely to endurance. There are no continuous pathways, no gradual gradients of increasing density or supportive structure that might guide a vessel from one star to another. Instead, there is a near uniform vacuum punctuated by isolated gravitational fields. Each star exerts its influence across a limited region, but between these regions lies a vast neutral zone where no dominant force assists movement. A spacecraft moving through this region would spend most of its journey far from any significant gravitational anchor, continuing on inertia once initial acceleration is complete. The absence of external support means that every stage of motion must be self-contained with no environmental assistance to adjust trajectory or speed. The scale of distance also reshapes the meaning of speed. In everyday context, speed is measured against familiar reference points such as walking, driving, or orbital motion. In interstellar space, these references lose relevance. Even the fastest human-made objects traveling at tens of kilometers per second require thousands of years to traverse distances between nearby stars. This mismatch between velocity and separation introduces a fundamental limitation that is not purely technological but structural. The universe at this scale does not provide enough time or continuity for conventional motion to produce meaningful relocation between star systems within a human lifetime. The structure of the interstellar medium itself contributes additional subtle resistance. Although extremely thin, it is not entirely empty. High-energy particles, stray atoms, and microscopic dust grains drift through this space at high relative speeds. Over long durations, even sparse material can accumulate effects on a moving object. At higher velocities, collisions with these particles become increasingly significant, converting the emptiness into a source of gradual erosion and energy loss. The region that appears empty at low resolution becomes an active environment when examined through the lens of sustained high-speed travel. Gravity in this outer region is also diffuse. While each star exerts a strong local influence, the combined gravitational field of the galaxy creates a gentle overall structure that shapes orbital paths over long periods. However, this structure does not provide direct assistance for travel between stars. Instead, it defines large-scale motion patterns that operate over millions of years, far beyond the timescale of any planned journey. A spacecraft moving through this region would still need to overcome local gravitational wells and then drift through extended zones where gravitational influence is weak and unhelpful for navigation. Time itself becomes intertwined with distance in a way that alters the meaning of travel. This separation between stars ensures that any journey unfolds across generations, not individual lifetimes. Even if propulsion systems improve significantly, the outer structure of space imposes a temporal expansion on all movement. The journey is not simply long. It becomes detached from the biological and cultural timescales that define human continuity. Information intention and observation all become stretched across durations that exceed stable social structures. In this region, the concept of arrival loses immediate relevance. The destination exists as a distant point of light, unchanged in appearance across long spans of time, while the traveller experiences constant isolation from familiar reference points. The surrounding space offers no intermediate markers of progress, no accumulation of nearby objects to indicate movement. Instead, the journey proceeds through an environment that remains visually and physically consistent, reinforcing the perception of stillness even during continuous motion. The outer interstellar region therefore establishes the foundational condition that underlies all later limitations. It is not hostile in an active sense, but its emptiness, scale, and temporal structure create a framework in which movement between stars becomes inherently constrained. The absence of structure is itself the defining feature shaping every attempt at traversal, long before considerations of propulsion energy or survival become relevant. In this space, distance is not a simple separation, but the dominant physical reality that governs what motion can mean at all. Chemical propulsion represents the earliest practical method by which humanity moves beyond the surface of a planet, relying on the controlled release of energy stored in molecular bonds. In this outer region of technological limitation, motion is produced by burning propellant and expelling mass in the opposite direction, creating thrust-through reaction. The principle is straightforward, grounded in Newtonian mechanics, where every action produces an equal and opposite reaction. Yet the simplicity of the principle hides the strict constraints imposed by the amount of energy available within chemical reactions and the finite mass that must be carried to generate that energy. The energy stored in chemical bonds is limited by the structure of atoms themselves. When fuel and oxidizer combine, electrons shift between molecular configurations, releasing energy in the form of heat and expanding gases. This energy is sufficient to lift material from planetary surfaces and place it into orbit, but it is small when compared with the energy required to approach even a small fraction of the speed of light. The exhaust velocities produced by chemical rockets typically reach only a few kilometers per second, which is enough for orbital maneuvers but remains insignificant on interstellar scales. Within this framework, propulsion depends not only on energy release, but also on the need to carry both fuel and the reaction mass. This creates a structural limitation where increasing velocity requires increasing fuel, which in turn increases total mass, which then requires even more fuel to accelerate. The relationship becomes increasingly inefficient as velocity increases, forming a recursive burden on system design. Even the most advanced chemical engines face this constraint, where a large portion of the vehicle must be dedicated not to payload but to propellant that is consumed early in the journey. As a spacecraft attempts to gain speed, the proportion of its mass devoted to fuel grows rapidly. This creates a diminishing return where each additional increment of velocity requires disproportionately larger amounts of propellant. The result is a practical ceiling on achievable speeds. Beyond a certain point, the mass required to carry enough chemical fuel becomes so large that construction and launch become unfeasible. This ceiling is not determined by engineering skill alone, but by the fundamental energy density of chemical reactions. The exhaust produced in chemical propulsion also carries thermal and mechanical limitations. The gases expelled from combustion chambers expand rapidly, but they cannot exceed the energy available from molecular rearrangement. This sets an upper bound on exhaust velocity, which directly influences the efficiency of momentum transfer. Without higher exhaust velocities, the ability to accelerate efficiently over long durations remains restricted. As a result, most chemical propulsion systems operate within a narrow band of performance that is well understood and highly optimized, yet fundamentally insufficient for extreme interstellar motion. Another constraint arises from structural stress. As propulsion systems scale up in size to accommodate more fuel, the mechanical forces within the vehicle increase. Tanks must withstand pressure differences, combustion instability, and vibrational forces that grow with thrust. Materials used in construction have finite strength, and beyond certain thresholds, no known structural design can maintain integrity while supporting the required mass of propellant for extreme acceleration. This introduces a physical boundary that is independent of energy considerations alone. Chemical propulsion also interacts with gravitational environments in a limited way. Within planetary systems, it is highly effective for transitioning between orbital states, escaping gravity wells and performing controlled landings. However, once outside the influence of a planet or star, the absence of gravitational assistance means that all velocity must come from internal energy reserves. There is no external field to exploit for sustained acceleration. The spacecraft becomes fully dependent on its initial fuel load, which must carry it through the entirety of its motion without replenishment. Over long durations, this dependence becomes increasingly restrictive. Even if a vehicle were launched with a large supply of chemical propellant, the exponential relationship between mass and required fuel quickly consumes any advantage. Small increases in desired speed result in disproportionately large increases in fuel requirements, and this scaling behavior prevents chemical propulsion from bridging interstellar distances within meaningful timeframes. The limitation is not simply one of scale, but of exponential growth in resource demand. Temperature and energy conversion efficiency further reduce the usable portion of chemical energy. Not all released energy is converted into directed motion. A significant fraction is lost as heat radiation and turbulent flow within exhaust plumes. These inefficiencies accumulate across all stages of propulsion, reducing the effective output compared with theoretical maximums. Engineering improvements can reduce losses, but they cannot eliminate them entirely due to the nature of thermodynamic processes. In practice, chemical propulsion operates within a stable but narrow envelope of performance that defines early spaceflight capability. It enables access to near-planetary space and limited exploration of nearby celestial bodies. However, when extended conceptually to interstellar distances, the same mechanisms reveal their insufficiency. The energy scale required to cross the distances between stars exceeds chemical energy availability by many orders of magnitude, creating a gap that cannot be bridged by incremental improvements alone. The structure of chemical propulsion therefore defined a boundary in motion capability. It is a boundary rooted in atomic scale energy storage rather than engineering design. While it enables initial departure from planetary surfaces, it does not provide a pathway to sustained high-speed travel across interstellar space. Instead, it establishes the first clear limitation in the progression from local movement to cosmic traversal, where the scale of required energy begins to exceed the physical chemistry of matter available in conventional fuels. This limitation remains constant regardless of external conditions. Whether operating in vacuum or within atmosphere, the same energy constraints apply. The absence of air resistance in space does not improve efficiency beyond initial acceleration phases, because the limiting factor is not drag but energy availability and exhaust velocity. Once fuel is expended, motion continues only through inertia, with no further acceleration possible. This inertial phase dominates long-distance travel and determines final achievable speeds. Within the broader structure of interstellar travel, chemical propulsion defines the earlier stage of capability and simultaneously marks the beginning of fundamental limitation. It provides motion, but not sufficient continuity of acceleration to overcome vast spatial separations. The transition from powered motion to inertial drift becomes inevitable, and once this transition occurs, no further increase in speed is possible without a different class of energy source. The outer structure of space then dominates the trajectory, entirely shaping movement through distance rather than propulsion. The region defined by relativistic limits introduces a boundary that is not constructed from distance or material conditions, but from the structure of space-time itself. In this layer, motion is governed by rules that differ from everyday experience, where time and space are interwoven into a single framework. As speed increases, time for the moving system begins to behave differently relative to external observers, and spatial measurements contract along the direction of motion. These effects are not abstract corrections, but measurable consequences of relativistic physics, confirmed through particle experiments and precise astronomical observations. At low speeds, the effects of relativity are negligible, and classical motion remains an accurate description. However, as velocity approaches a significant fraction of the speed of light, these corrections become dominant. The speed of light itself acts as a universal limit, not because objects are prevented from accelerating in a mechanical sense, but because the energy required to continue accelerating increases without bound. Each additional increment of speed requires more energy than the previous one, and this requirement grows steeply as the limit is approached. Within this region, time dilation becomes significant. A moving observer experiences time passing more slowly, relative to a stationary reference frame. This effect has been observed in high-speed particles such as muons, created in the upper atmosphere, which survive longer when moving at relativistic speeds than they would at rest. While this phenomenon allows particles to travel farther than expected before decaying, it does not provide a method to bypass the energy constraints that prevent macroscopic objects from reaching similar speeds without extreme resource requirements. Length contraction also emerges as a natural consequence of high-speed motion. Distances measured along the direction of travel appear shorter to the moving system. From the perspective of a spacecraft approaching relativistic speeds, the distance to a distant star would seem reduced. However, this contraction does not reduce the energy required to accelerate to that speed from an external frame of reference. Instead, it reflects the internal consistency of space-time geometry, ensuring that all observers regardless of motion agree on physical laws even if measurements differ. As velocity increases further, the effective mass of the system increases in terms of energy equivalence. This does not mean that matter literally gains rest mass, but that additional energy is required to continue acceleration, as if the system becomes increasingly resistant to change in velocity. This resistance grows dramatically near the speed of light, making further acceleration progressively more difficult. The closer an object approaches this limit, the more energy is required for even the smallest increase in speed. In this region, the concept of reaching the speed of light becomes unattainable for objects with mass. No finite amount of energy can accelerate a massive object to this limit, because the required energy approaches infinity as velocity approaches the speed of light. This creates a strict boundary in motion through space-time not imposed externally, but arising from the geometry of the universe itself. Photons, which are massless, move at this speed naturally, but they cannot be slowed without changing their fundamental nature. For macroscopic travel, this limit defines a hard ceiling on velocity. Even with advanced propulsion systems far beyond chemical rockets, the same relativistic structure applies. The energy cost of approaching light speed becomes prohibitive long before the limit is reached. This means that interstellar travel cannot rely on simply increasing speed indefinitely. Instead, it must operate within a constrained band far below this universal boundary. The implications of this limit extend beyond propulsion into navigation and mission design. At relativistic speeds, even small particles in space become dangerous. Dust grains that would be harmless at lower velocities carry enormous kinetic energy when impacted at near light speed, effectively transforming the vacuum into a field of high-energy collisions. The interstellar medium, though extremely sparse, becomes a significant hazard when viewed through the lens of relativistic motion. Electromagnetic radiation also shifts in character under these conditions. Light from the direction of motion becomes blue-shifted, increasing in energy, while light from behind becomes red-shifted. This alters the radiation environment experienced by a fast-moving object, concentrating energy into a forward-facing field. These changes add further complexity to sustaining high-speed travel, as shielding must account for altered spectral distributions and intensified radiation exposure. Communication is also affected by relativistic motion. Signals sent from a rapidly moving spacecraft experience time distortions and frequency shifts, complicating real-time interaction with distant observers. As speed increases, the delay and distortion between reference frames grow, making coordinated control increasingly difficult. Even if travel were physically possible at extreme speeds, maintaining operational coherence becomes progressively more complex. Within this relativistic region, motion is no longer simply a matter of propulsion, but a negotiation with spacetime itself. Every increase in velocity alters the structure of time, energy, and distance in ways that reinforce the same boundary. The speed of light emerges not as an engineering target, but as a structural constant embedded in the geometry of the universe. It defines the outer edge of accessible motion for anything with mass. This boundary does not depend on technological level. It remains unchanged regardless of advances in energy production or material science. It is a property of space-time that applies uniformly across all regions of the universe. As a result, it establishes a universal constraint on how quickly information and matter can propagate, shaping not only travel, but the fundamental connectivity of physical systems. The relativistic region therefore marks a transition from practical engineering limits to fundamental physical law. It defines the point at which increases in energy no longer translate into proportional increases in velocity. Instead, energy is absorbed into the structure of space-time itself, preventing further acceleration beyond a finite limit. This condition ensures that while motion across interstellar distances is theoretically possible, it cannot exceed the strict boundaries imposed by the speed of light. Energy requirements for motion through space expand in a way that does not follow linear intuition. In the outer region of interstellar travel concepts, it is often assumed that reaching higher speeds requires proportionally more energy, yet the underlying structure of relativistic physics shows a sharper escalation. As velocity increases towards significant fractions of the speed of light, each incremental gain in speed demands disproportionately larger amounts of energy. This escalation is not a technical inefficiency, but a direct consequence of how energy and motion are linked in space-time. At low velocities, kinetic energy increases smoothly with speed, and the relationship appears manageable within engineering constraints. However, as velocity rises, relativistic effects begin to dominate, and the energy required to continue accelerating grows steeply. This growth is not capped by any practical engineering limit, but instead approaches a mathematical divergence as the speed of light is approached. The closer an object moves toward that boundary, the more energy is required for smaller and smaller increases in velocity, creating a curve that rises sharply without flattening. Within this region, the concept of energy becomes deeply tied to the structure of motion itself. Energy is not only what enables acceleration, but also what contributes to the effective resistance against further acceleration. As a result, energy input is increasingly absorbed into the system without producing equivalent gains in velocity. This creates a condition where enormous amounts of energy produce only marginal improvements in speed, especially at the upper limits of attainable motion. The implications of this scaling behavior become clear when considering interstellar distances. Even reaching a small fraction of the speed of light requires energy far beyond the total consumption of entire planetary civilizations over long periods. This comparison is not symbolic, but reflects the quantitative mismatch between available energy sources and the demands of relativistic travel. The gap between what is needed and what is accessible expands rapidly as speed increases. Energy sources available to known physics, including chemical nuclear fission and nuclear fusion, each occupy different scales of energy density. Chemical energy is relatively low and is already insufficient for high-speed interstellar motion. Nuclear fission provides a greater energy density, but remains far below what is required for sustained relativistic travel. Nuclear fusion, while more efficient in converting mass into energy, still falls short of the energy scale required to approach significant fractions of light speed for macroscopic objects. Each step up in energy density narrows the gap but does not close it. The concept of matter-energy conversion introduces a higher theoretical ceiling, where mass itself becomes a direct energy source. Even in this case, only a small fraction of mass can realistically be converted into usable energy under known physical processes. This limitation means that even the most efficient processes available in nature cannot fully bridge the energy gap required for interstellar travel at relativistic speeds. As energy demands increase, inefficiencies in conversion and utilization become more significant. No energy system operates at perfect efficiency, and losses occur at every stage of transformation. Heat dissipation, radiation loss, and incomplete reaction cycles reduce the usable portion of input energy. Over long-duration propulsion, these inefficiencies accumulate, further widening the gap between theoretical energy availability and practical output. In addition to generation, energy storage presents another limitation. Large-scale energy storage systems must contain and manage immense amounts of energy without structural failure. At high energy densities, materials face stability limits, and containment becomes increasingly difficult. Even if energy could be generated in sufficient quantities, safely storing and releasing it in controlled ways introduces another layer of constraint. The distribution of energy over time also plays a critical role. Interstellar travel requires sustained acceleration, or at least carefully managed velocity profiles over long durations. This means that energy cannot be used in short bursts alone. It must be delivered steadily over extended periods. Maintaining such continuity of energy delivery without interruption or degradation introduces logistical challenges that grow with mission scale. As velocity increases, the energy required for additional acceleration begins to resemble a threshold rather than a gradual cost. Beyond certain points, the energy needed for meaningful speed gains becomes so large that it exceeds any practical accumulation of resources. This creates a functional boundary where additional investment yields negligible improvement in travel time. The structure of space itself contributes indirectly to this limitation. Because interstellar distances are vast, even small reductions in travel time require large increases in velocity. However, the energy required to achieve those increases grows faster than the benefit gained in reduced travel duration. This imbalance creates a diminishing return that strengthens as distances increase. In this region, energy is no longer simply a resource, but becomes the central limiting factor defining motion. It governs not only how fast an object can travel, but whether sustained high-speed travel is possible at all. Even theoretical advances in propulsion cannot escape the underlying scaling relationship between energy and velocity imposed by relativistic physics. The result is a landscape where energy requirements expand faster than technological progress can realistically supply. No matter how efficient a system becomes, it must still operate within the same physical framework where energy costs rise steeply near the speed of light. This ensures that interstellar travel remains constrained not by a single barrier, but by a continuously increasing demand that outpaces available means. Within this framework, energy does not merely enable motion, it defines its outer boundary. The structure of the universe enforces a relationship where distance, speed, and energy are inseparably linked. As a result, the dream of rapid interstellar travel encounters a limit that is not static but dynamically reinforced by the nature of space-time and energy itself. Beyond planetary protection, space becomes an environment where radiation is no longer filtered by atmosphere or magnetic fields. In this outer region of interstellar exposure, high-energy particles move freely through the galaxy, originating from stellar activity, supernova remnants, and distant energetic processes. These particles include protons, atomic nuclei, and high-energy electrons, all traveling at extreme speeds through otherwise sparse space. Without atmospheric shielding, any object entering this environment is continuously exposed to ionizing radiation that accumulates effects over time. Radiation in this context is not a single phenomenon, but a continuous background composed of multiple sources. Galactic cosmic rays originate outside the solar system and consist of highly energetic charged particles that penetrate deeply into matter. Solar energetic particles originate from the Sun during periods of magnetic activity, adding variability to the radiation environment. Together, these sources create a persistent field of energy that interacts with any material placed in space for extended periods. When these particles encounter matter, they transfer energy through collisions at atomic scales. This process can disrupt molecular structures, ionize atoms, and break chemical bonds. In living systems, such disruptions affect biological molecules including DNA and proteins. Over short durations, biological repair mechanisms can correct some of this damage, but in long-term exposure, the rate of damage can exceed the capacity for repair, leading to cumulative degradation. Outside planetary protection, this radiation environment remains constant and unavoidable. There is no natural shielding in interstellar space, comparable to the dense atmosphere of a planet or the magnetic field that deflects charged particles around Earth. As a result, any long-duration travel must account for continuous exposure to this energetic background. The intensity may vary depending on location within the galaxy, but it never disappears entirely. At higher velocities, the effects of radiation exposure become more complex. Due to relativistic motion, incoming particles can appear more energetic in the frame of the moving object. This increases the effective intensity of radiation from the forward direction of travel. Even sparse particles in interstellar space can become significant hazards when their relative energy increases due to high-speed encounters. The interaction between motion and radiation therefore creates a feedback condition where increasing speed amplifies exposure risk. Shielding against radiation introduces its own structural constraints. Materials capable of absorbing or deflecting high-energy particles must have sufficient density and thickness to reduce penetration. However, increasing shielding mass adds to the overall mass of a spacecraft, which in turn increases the energy required for acceleration. This creates a direct trade-off between protection and mobility, where improving safety reduces efficiency of travel. Some forms of shielding rely on magnetic or electromagnetic fields to deflect charged particles. These systems require continuous energy input to maintain field strength and stability. While they can reduce exposure to certain types of radiation, they are less effective against neutral particles and high-energy photons, which can pass through magnetic fields without deflection. As a result, no single shielding strategy provides complete protection in the interstellar environment. Biological systems are particularly sensitive to cumulative radiation exposure. Cells rely on stable molecular structures to function, and repeated ionization events can lead to mutations or loss of function. In controlled environments on Earth, radiation exposure is limited and managed through natural and artificial shielding. In interstellar space, maintaining similar protection levels becomes increasingly difficult due to the constant background presence of energetic particles. Over long durations, radiation exposure affects not only individual organisms but also electronic systems. Semiconductor materials used in spacecraft electronics can experience charge displacement and structural disruption under sustained particle bombardment. This can lead to memory errors, system degradation, and eventual failure, if not mitigated through redundancy or shielding. As missions extend in duration, maintaining system integrity becomes progressively more complex. The distribution of radiation in space is not uniform. Certain regions, such as those near supernova remnants or active galactic environments, contain higher concentrations of energetic particles. However, even in relatively quiet regions, a baseline level of cosmic radiation persists. This means that no trajectory through interstellar space is entirely free from exposure, only varying in intensity. As distance increases, the cumulative effect of radiation becomes more significant than its instantaneous intensity. A short exposure may produce minimal damage, but over extended periods, even low levels of radiation accumulate into substantial effects. This time-dependent accumulation means that interstellar travel introduces not only spatial distance, but also prolonged exposure to a persistent energetic environment. The interaction between radiation and matter also produces secondary particles. When high-energy cosmic rays strike atomic nuclei, they can generate cascades of additional particles, further increasing the complexity of the radiation field. These secondary interactions extend the reach of radiation effects beyond the initial point of contact, creating a chain of energetic events within materials. In this region of space, radiation is not an occasional hazard but a defining environmental condition. It shapes the requirements for shielding, influences structural design, and limits biological viability over time. Even with advanced protective systems, complete elimination of exposure remains unattainable under known physical principles. The presence of radiation therefore establishes another layer of constraint on interstellar travel. It does not prevent motion directly, but imposes cumulative limits on duration, safety, and system stability. Combined with distance energy and relativistic constraints, radiation contributes to a multi-layered environment in which long-term survival becomes increasingly difficult to sustain. Within extended microgravity environments, the absence of sustained gravitational loading becomes a defining physical condition that gradually reshapes biological systems. In this region of experience, matter behaves normally at the atomic level, yet large-scale structures that evolved under constant gravity begin to adjust in ways that are slow, cumulative, and difficult to reverse. The human body adapted to a planetary surface where weight continuously acts on every tissue enters a state where that constant force is removed and internal systems begin to reorganize according to new mechanical realities. Muscle tissue is one of the first systems affected. On a planet, muscles continuously work against gravity even during simple posture and movement. In microgravity, this constant resistance is reduced, and muscle fibers receive less mechanical stimulus. Over time, this leads to gradual weakening where muscle mass decreases and strength declines. The process is not immediate but accumulates over weeks and months, reflecting the body's adaptive nature rather than sudden failure. Without consistent counteracting forces, the biological investment in maintaining strong muscular structure is reduced. Bone structure undergoes a similar adjustment. Bones are living tissues that constantly remodel in response to mechanical stress. On Earth, weight-bearing activities signal the need for maintaining density and strength. In microgravity, this signal diminishes, and bone resorption begins to exceed bone formation. Minerals such as calcium are gradually released into the bloodstream, altering internal balance and increasing vulnerability to fractures over long durations. This change is particularly significant in weight-bearing regions of the skeleton, where structural adaptation is most pronounced under normal gravity. Fluid distribution within the body also shifts. Without gravity pulling fluids downward, bodily fluids redistribute more evenly toward the upper regions of the body. This can lead to changes in pressure within the head and cardiovascular system. The human circulatory system, which evolved under constant gravitational gradients, must adjust to a new equilibrium where fluid movement is no longer vertically biased. These adjustments affect vision pressure regulation and overall physiological stability. The cardiovascular system itself responds to reduced workload. In the absence of gravity-driven blood pooling, the heart does not need to pump against the same hydrostatic pressure gradients. Over time, this can lead to changes in cardiac muscle structure and efficiency. The system remains functional, but its long-term adaptation under microgravity conditions introduces subtle shifts in performance that become more noticeable during re-exposure to planetary gravity. At the cellular level, microgravity influences gene expression and cellular signaling pathways. Cells respond to mechanical forces in their environment, and when these forces change, internal regulatory processes adjust accordingly. Some cellular functions may slow, while others adapt to maintain stability in altered conditions. These changes are complex and not fully predictable, reflecting the sensitivity of biological systems to physical context. The immune system also experiences variation under extended weightlessness. Observations from space missions indicate alterations in immune response efficiency, though the mechanisms are still being studied. Stress radiation exposure and microgravity together contribute to a combined environmental condition that differs significantly from Earth-based life. This makes long-term biological stability more difficult to maintain without continuous medical and environmental support. Beyond individual systems, coordination between bodily systems becomes increasingly important. The human body operates as an integrated network where muscular, skeletal, cardiovascular, and nervous systems interact continuously. When one component adapts to microgravity, others respond in interconnected ways. This interconnected adaptation can lead to cascading changes that require careful management in long-duration environments. Artificial countermeasures attempt to replicate gravitational effects through rotation or mechanical loading. These systems create simulated forces that help maintain muscle and bone integrity. However, they introduce complexity in spacecraft design and require continuous operation. Even with such systems in place, complete replication of natural gravity is difficult to achieve, and some degree of physiological change still occurs over extended time. Psychological effects emerge alongside physical adaptation. The absence of natural environmental cues associated with gravity horizon and stable up-down orientation can influence perception and cognitive state. Over long periods, isolation from planetary environments and limited spatial variation contribute to changes in sleep patterns, attention, and emotional regulation. These effects are not isolated but interact with physical conditions to shape overall well-being. The combination of physiological and psychological adaptation defines microgravity as more than a mechanical condition. It becomes a full environmental system affecting all aspects of human biology. Even in controlled spacecraft environments, maintaining long-term stability requires continuous intervention, monitoring, and adjustment. The body does not remain static in such conditions, but continuously adapts in response to altered physical constraints. As duration increases, the cumulative nature of these changes becomes more significant. Short-term exposure can be managed with minimal long-term consequences, but extended periods reveal the full scope of adaptation required. The body remains functional, yet its baseline state gradually shifts away from planetary norms, creating a divergence that must be corrected upon return to gravity. Within the broader context of interstellar travel, microgravity represents a slow but persistent form of transformation. It does not destroy function immediately, but alters it progressively. Combined with radiation energy constraints and relativistic limitations, it contributes to a layered set of challenges that define the difficulty of sustaining human life beyond planetary environments for extended durations. Life support systems in space operate as closed ecological frameworks designed to replicate the essential environmental conditions that naturally exist on a planetary surface. In this region of artificial habitation, air, water, and food are no longer part of an open planetary cycle, but must be continuously recycled within a confined structure. Every component becomes part of an interconnected system, where stability depends on maintaining balance across multiple tightly regulated processes. Unlike natural environments, there is no external reservoir to absorb error or replenish loss, making the system inherently sensitive to disruption. Air recycling forms the foundation of this controlled environment. Oxygen is consumed by biological processes and must be regenerated through chemical or biological systems. Carbon dioxide produced by respiration must be removed and either stored or converted back into usable forms. In controlled environments, processes such as chemical scrubbers or plant-based photosynthesis systems perform this function. Each method has limitations requiring careful calibration to ensure that gas concentrations remain within safe ranges over extended periods. Water recycling is equally critical. In a closed system, water is not continuously replenished but reused through filtration and purification cycles. Moisture from respiration, perspiration, and waste streams is collected and processed back into potable form. This cycle must operate with high efficiency, as even small losses accumulate over time. Any inefficiency in recovery reduces total available supply, creating long-term sustainability concerns that become more pronounced during extended missions. Food production introduces additional complexity. Biological food systems rely on growth cycles that require energy, nutrients, and stable environmental conditions. In space-based systems, food may be stored for long durations or partially produced through controlled agricultural processes. Plant growth systems must balance light, water, and nutrient delivery within confined spaces. These systems are sensitive to variation, and small disruptions in environmental control can affect yield and stability. Waste management is another essential component of life support. Biological and material waste must be processed in ways that prevent contamination and resource loss. In closed systems, waste is not discarded, but treated as a potential input for recycling processes. Organic waste may be broken down and reused within agricultural systems, while other materials require mechanical or chemical processing. The efficiency of this recycling loop directly influences overall system sustainability. The interdependence of these subsystems creates a tightly coupled network. A disruption in one area can propagate through others, producing cascading effects. For example, a reduction in water recovery efficiency affects plant growth, which in turn affects oxygen production and carbon dioxide absorption. These feedback relationships require continuous monitoring and correction to maintain stability. Energy input supports every aspect of life support operation. Filtration systems, circulation pumps, lighting for plant growth, and thermal regulation all depend on a consistent energy supply. In space environments, this energy is typically derived from solar panels or nuclear systems. Any interruption in energy flow directly affects the entire ecological balance, making energy reliability a central requirement for survival. Thermal regulation is also critical within closed habitats. Heat is generated by human activity, electronics, and life support systems themselves. In the vacuum of space, heat cannot dissipate naturally through convection, so it must be managed through radiation systems. Radiators expel excess heat into space, maintaining stable internal temperatures. If this balance is disrupted, systems can overheat or become too cold, both of which affect biological and mechanical function. Microbial control is another important aspect of closed environments. Microorganisms are both essential and potentially hazardous. They participate in biological recycling processes, but can also proliferate in uncontrolled ways. Maintaining microbial balance requires careful environmental regulation and monitoring. Over long durations, even small imbalances can lead to significant system changes requiring corrective intervention. Human presence introduces additional variability into life support systems. Metabolic rates, activity levels, and individual biological differences all influence resource consumption and waste production. This variability must be accounted for in system design to ensure stability across different operational conditions. Predictive models are used to estimate consumption patterns, but real-world variability always introduces some degree of uncertainty. Redundancy is a fundamental design principle in these systems. Multiple independent pathways for air, water, and energy processing are often included to reduce the risk of total system failure. If one component fails, others can compensate temporarily. However, redundancy increases system complexity and mass, which in turn affects propulsion and energy requirements for transport systems. Long-duration operation reveals the cumulative stress on all life support components. Filters degrade, mechanical parts wear down, and biological systems shift in response to subtle environmental changes. Maintenance and repair become essential functions rather than optional support activities. Without regular intervention, system efficiency declines, gradually increasing the risk of instability. In this region of artificial environmental dependence, life does not exist independently, but as a managed condition maintained by continuous technological support. Every aspect of survival is mediated through engineered systems that must function without interruption over long periods. The absence of external planetary cycles means that all regulation must be internal, creating a closed loop of dependence on machinery and controlled processes. Within the broader context of interstellar travel, life support systems represent one of the most delicate constraints. Even if propulsion and energy challenges are addressed, sustaining stable environmental conditions over decades or centuries introduces a separate and equally complex limitation. The system must not only function initially, but remain stable across long durations with minimal degradation in an environment where repair opportunities are limited and failure risks accumulate over time. Materials used in spacecraft construction exist in an environment that is fundamentally different from planetary conditions. In this region of vacuum and radiation, matter is no longer supported by atmospheric pressure or protected by environmental buffering. Instead, every surface is directly exposed to extreme temperature variation, high-energy particles, and long-duration structural stress. Over time, these factors interact with material properties in ways that gradually alter their integrity even without visible damage in the early stages. Vacuum conditions remove the stabilizing influence of atmospheric pressure. On Earth, materials exist within a surrounding medium that moderates heat exchange and mechanical stress. In space, there is no surrounding air, so heat transfer occurs only through radiation. This changes how materials respond to temperature fluctuations, especially when moving between sunlight and shadow. Surfaces exposed to direct solar radiation can heat rapidly, while shaded regions cool just as quickly, creating repeated thermal cycling. This thermal cycling produces expansion and contraction within material structures. Different components of a spacecraft may expand at different rates, depending on their composition, leading to internal stress at joints and interfaces. Over long durations, these repeated cycles can lead to fatigue, where microscopic structural changes accumulate. Even if the material remains visually intact, internal bonds may gradually weaken due to repeated mechanical strain. Radiation exposure further alters material structure at the atomic level. High-energy particles can displace atoms within solid lattices, creating defects in crystalline structures. These defects accumulate slowly but steadily, changing mechanical properties such as strength, flexibility, and conductivity. In electronic materials, radiation can disrupt charge pathways, affecting performance and reliability. Shielding can reduce but not fully eliminate this exposure. Ultraviolet radiation from the sun contributes additional degradation. Without atmospheric filtering, ultraviolet photons interact directly with surface materials. This can break chemical bonds, especially in polymers and organic compounds, leading to embrittlement or surface erosion. Over time, exposed surfaces may lose elasticity and become more brittle, increasing the risk of cracking under stress. Micrometeoroids and dust particles represent another source of mechanical erosion. Although space is extremely sparse, small particles travel at high velocities relative to spacecraft. When these particles impact a surface, they transfer kinetic energy that can cause localized damage. Over long durations, repeated impacts create pitting and surface roughness, gradually altering aerodynamic and structural properties. Material fatigue in space is not governed by a single dominant factor, but by the combined influence of multiple environmental stresses. Thermal cycling, radiation exposure, and particle impacts interact in complex ways. A material that performs well under one condition may degrade more quickly when multiple factors are present simultaneously. This combined stress environment requires careful material selection and engineering design. Metals used in spacecraft must balance strength, weight, and resistance to environmental degradation. Aluminum alloys, titanium, and specialized composites are commonly used due to their favorable properties. However, even these materials are not immune to long-term changes. Grain structure evolution, microfracture formation, and surface oxidation in limited environments can gradually reduce performance. Polymers and insulating materials face different challenges. Many polymers are sensitive to radiation and ultraviolet exposure, which can break molecular chains and alter flexibility. In space, protective coatings are often required to extend their operational life. Even with protection, gradual degradation remains unavoidable over extended periods. Lubrication systems also behave differently in vacuum. Conventional liquid lubricants may evaporate or break down, requiring specialized formulations or solid lubrication systems. Mechanical components that rely on moving parts must account for this difference, as frictional changes over time can affect performance and increase wear rates. Temperature extremes influence not only mechanical properties but also chemical stability. Some materials undergo phase changes or chemical reactions at temperatures encountered in space environments. Although these changes may be slow over long durations, they contribute to cumulative degradation that must be accounted for in system design. The absence of atmospheric oxygen reduces some forms of corrosion, but does not eliminate chemical interaction entirely. Outgassing, where trapped gases slowly escape from materials, can alter structural integrity and affect nearby components. This process is especially relevant in sealed systems where released gases may accumulate or contaminate sensitive equipment. Material degradation in space is therefore a slow, continuous process rather than a sudden failure event. Components often appear stable for long periods before showing signs of weakening. This delayed manifestation makes long-term prediction difficult and requires conservative design approaches with significant safety margins. Maintenance and repair capabilities become essential for extending operational life. In environments where replacement is impossible, systems must either be designed for extreme durability or include methods for in situ repair. However, repair itself is limited by available materials and tools, creating constraints on how effectively degradation can be managed over time. Within the broader context of interstellar travel, material stability becomes a critical limiting factor. Even if propulsion energy and life support systems function effectively, the gradual erosion of structural integrity introduces uncertainty over long durations. A spacecraft must remain intact not only at launch, but across extended periods in an environment that continuously acts to weaken its components. This region of space does not destroy materials abruptly, but continuously reshapes them at microscopic levels. Over long timescales, these small changes accumulate into meaningful structural differences, gradually reducing reliability. The challenge is not a single catastrophic force, but a persistent environment that slowly alters every exposed surface. Within interstellar space, the presence of matter is extremely sparse, yet not entirely absent. In this region, tiny particles of dust and isolated atoms drift through vast volumes, distributed unevenly across the galaxy. Although the density is low, the relative speeds involved in spacecraft travel transform even rare particles into significant hazards. What appears empty at rest becomes dynamically active when motion is introduced at high velocity, creating an environment where impact energy rather than mass becomes the defining factor. Interstellar dust consists of microscopic grains formed from heavier elements produced in stellar interiors and distributed through stellar winds and supernova events. These grains vary in composition, often containing silicates, carbon-based structures, and metallic compounds. Their sizes are typically extremely small, yet their physical presence is persistent across galactic space. Over time, they become part of a diffuse medium that fills the gaps between stars. At low relative speeds, these particles pose little threat. However, as velocity increases, the kinetic energy associated with even a single dust grain rises dramatically. Energy scales with the square of velocity, meaning that small increases in speed produce large increases in impact energy. At high fractions of the speed of light, collisions with particles that would otherwise be negligible become capable of causing significant structural damage. The distribution of interstellar particles is not uniform. Some regions contain higher concentrations of dust due to local stellar activity, while others are more rarefied. However, even in the most empty regions, the probability of encountering particles over long distances remains non-zero. Over interstellar scales, cumulative exposure becomes inevitable even if individual encounters are rare. When a high-speed spacecraft encounters a particle, the interaction occurs in extremely short timescales. The energy of impact is transferred almost instantaneously into localized heating shock waves and material disruption. At sufficiently high velocities, the impact can vaporize both the particle and a portion of the spacecraft's surface, producing secondary particles that further contribute to material erosion. Repeated exposure to such impacts creates a gradual degradation pattern. Surfaces become pitted, eroded, and structurally weakened over time. This process does not require large particles. Even microscopic grains contribute when multiplied across vast travel distances. The cumulative effect becomes a defining constraint on sustained high-speed motion through interstellar space. Shielding strategies can reduce but not eliminate this risk. Front-facing protective layers may absorb initial impact, sacrificing material to protect deeper structures. These sacrificial layers must be periodically replenished or designed with sufficient thickness to last the duration of a journey. However, increasing shielding thickness also increases mass, which in turn raises energy requirements for acceleration, creating a trade-off between protection and propulsion efficiency. At relativistic speeds, particle impacts take on additional complexity. Even hydrogen atoms, which are the most common constituents of interstellar space, carry significant energy when encountered at near-light velocity. These collisions can produce ionization cascades and secondary radiation, adding both mechanical and electromagnetic stress to spacecraft systems. The forward-facing direction of motion becomes a concentrated zone of risk. As velocity increases, incoming particles appear increasingly energetic and densely packed due to relativistic effects. This creates a directional hazard that intensifies with speed, requiring increasingly sophisticated shielding approaches. The environment ahead of a fast-moving object is not static, but dynamically transformed by the motion itself. Dust particles also interact with electromagnetic fields and plasma environments surrounding spacecraft. High-speed impacts can generate charged particles, which may accumulate or interact with onboard systems. Over time, this creates additional complexity in managing both physical and electrical stability within the spacecraft environment. The cumulative nature of these interactions distinguishes interstellar dust from other environmental factors. A single impact may be insignificant, but over millions or billions of kilometers, the repeated accumulation of small events becomes structurally meaningful. This gradual accumulation is central to understanding why long-duration travel through interstellar space presents increasing risk, even in seemingly empty regions. Thermal effects from impacts further contribute to degradation. Each collision converts kinetic energy into heat, which is localized but intense. Repeated heating cycles in small regions of material can weaken structural bonds and create microfractures, Over time, these microfractures may propagate, affecting larger sections of material integrity. Detection of interstellar particles is challenging because of their small size and sparse distribution. Most spacecraft cannot actively avoid them due to the unpredictability and low density of occurrence. Instead, designs focus on passive mitigation through shielding and material resilience rather than active avoidance strategies. In this region, motion itself becomes a source of environmental transformation. A stationary object would experience minimal interaction with interstellar dust, but a fast-moving object actively converts sparse matter into a continuous stream of high-energy interactions. This means that velocity does not simply traverse the environment but reshapes it from the perspective of the moving system. The long-term implications of this interaction extend beyond structural wear. They influence mission design speed limitations and the feasibility of sustained interstellar travel. Even if propulsion energy and biological systems were solved, the persistent presence of dust and particle impacts introduces a background constraint that scales with distance and velocity. Within the broader framework of interstellar travel limitations, dust and particle hazards represent a subtle but continuous force. They do not impose a single barrier, but instead contribute to a cumulative degradation process that grows with time and distance. This transforms interstellar space from a passive void into an active medium when viewed through the lens of sustained motion. Communication across interstellar distances is governed by the finite speed at which information can travel through space. In this outer region of separation, signals are carried primarily by electromagnetic waves, including radio and light, which move at the universal speed limit defined by space-time. This means that any exchange of information between a distant spacecraft and its origin point is fundamentally delayed not by technological inefficiency, but by the time required for signals to physically traverse the gap between locations. At distances within a planetary system, communication delays are short enough to feel immediate. Signals between Earth and nearby spacecraft can take seconds or minutes, allowing near real-time coordination. However, as distance increases to interstellar scales, these delays expand into years. A signal sent from a spacecraft near another star would take several years to reach its destination, and a response would require an equal amount of time to return. This transforms communication into a slow exchange rather than a continuous dialogue. In this region, information becomes temporally stretched. Each message carries the state of a system as it existed in the past, not its current condition. As distance increases, the gap between present reality and received information grows wider. This creates a condition where decision-making is based on outdated data, making real-time control impossible. Any system operating under these conditions must function with a high degree of autonomy. Autonomous operation becomes essential because external guidance cannot respond quickly enough to changing conditions. A spacecraft traveling to or between stars must be capable of managing its own systems, correcting errors, and adapting to unforeseen events without immediate external input. This requirement places significant demands on onboard computational systems and increases the complexity of mission design. Signal strength also decreases with distance. As electromagnetic waves propagate outward, their intensity spreads over larger areas, reducing the strength of the signal received at long range. Even with powerful transmitters, maintaining clear communication over interstellar distances requires sensitive receivers and efficient encoding methods. Noise from cosmic background radiation further complicates signal detection, as faint transmissions must be distinguished from natural electromagnetic activity. Bandwidth limitations become more pronounced as distance increases. The amount of information that can be reliably transmitted decreases due to signal degradation and the need for redundancy. Error correction becomes essential, but it also reduces effective data throughput. This creates a trade-off between reliability and communication speed, both of which are already constrained by distance. Relativistic motion introduces additional complexity. If a spacecraft is moving at high speed relative to its origin point, signals experience frequency shifts. Forward-facing signals become blue-shifted, while backward signals become red-shifted. These shifts alter the apparent frequency and energy of communication signals, requiring adjustments in encoding and decoding systems to maintain intelligibility. Time delay also affects synchronization. Coordinating events between two widely separated points becomes increasingly difficult when each side experiences information from the other in delayed intervals. Actions taken by one side may no longer align with the current conditions experienced by the other, leading to potential mismatches in timing and expectation. In extreme cases, communication becomes so delayed that the concept of coordinated mission control loses practical meaning. The spacecraft effectively becomes independent once it travels beyond a certain distance threshold, operating as a self-contained system with minimal real-time oversight. Earth-based operators can still send instructions and receive data, but these exchanges are slow and reflective rather than responsive. The psychological implications of this delay are also significant. For any human presence on board, communication with Earth becomes infrequent and increasingly disconnected from immediate experience. Messages received from home represent past states of life that may have already changed by the time they are read. This temporal separation alters the sense of connection between origin and destination. Noise in interstellar communication is not only electromagnetic but also structural. Plasma fields, cosmic radiation, and interstellar medium interactions can distort or interfere with signal propagation. These effects introduce uncertainty into received data, requiring additional correction and interpretation. Over long distances, the accumulation of such distortions increases the difficulty of maintaining clarity. Even with advanced communication technology, the speed of light imposes a strict limit on information transfer. No system can exceed this boundary, meaning that delays are unavoidable regardless of technological progress. This ensures that interstellar communication is always fundamentally asynchronous beyond a certain scale. Compression techniques and data prioritization become important tools for managing limited communication capacity. Only essential information can be transmitted efficiently, while less critical data must be stored or delayed. This selective transmission further contributes to the fragmented nature of interstellar information exchange. In this region of space, communication is no longer a continuous link but a sequence of delayed snapshots. Each message represents a historical state rather than a current reality. As distance increases, these snapshots become more separated in time, eventually forming a chain of disconnected updates rather than a fluid exchange. Within the broader context of interstellar travel, communication delay introduces a constraint that affects coordination, safety, and psychological continuity. Even if propulsion and life support challenges were overcome, the inability to maintain real-time connection with origin points creates a structural separation that cannot be eliminated. This separation becomes one of the defining features of any attempt to operate beyond the solar system. Psychological experience in prolonged isolation is shaped by the absence of familiar environmental, social, and temporal cues. In this region of extended separation from planetary life, the human mind continues to operate normally at short timescales, but gradually adjusts to conditions where external reference points become distant and infrequent. The structure of perception, memory, and emotional regulation remains intact, yet it is increasingly influenced by a stable but confined environment that changes very slowly over time. On a planetary surface, perception is continuously updated by varied stimuli, including changing weather, social interaction, and dynamic environments. In long-duration isolation, these variations are reduced and the environment becomes more predictable. Over time, the reduction in novelty can affect attention patterns, where the mind receives fewer external changes to process. This does not imply immediate impairment, but rather a gradual shift in how sensory information is prioritized and interpreted. The absence of immediate social proximity introduces another layer of separation. Human cognition is naturally adapted to regular interaction with others, where communication provides feedback, correction, and emotional grounding. In distant environments, communication delays mean that interaction becomes infrequent and asynchronous. Conversations lose immediacy and responses reflect past states rather than current conditions. This creates a structure where social continuity is preserved in form but altered in timing. Time perception itself becomes less anchored to external events. On Earth, time is structured by environmental cycles such as day and night seasonal variation and social schedules. In isolated environments, especially those far from planetary reference, these cycles may be artificially maintained or become less distinct. Without strong external markers, subjective time can begin to feel less segmented, with days blending into longer continuous intervals. Cognitive load also shifts under isolation. Tasks that require constant adaptation to changing environments are reduced, while systems monitoring and maintenance tasks become more prominent. This changes the balance of mental activity, emphasizing sustained attention over reactive decision-making. Over long durations, this can influence how concentration and alertness are distributed across time. Memory plays an important role in maintaining psychological continuity. In isolated environments, recollection of past experiences becomes a key reference point for maintaining a sense of progression. However, when communication with external environments is delayed, memories of external events may become temporally distant from current experience. This can create a layered perception of time where internal experience and external updates follow different rhythms. Emotional regulation remains stable in the short term but can be influenced by environmental monotony and social distance. Emotional responses are tied to both internal states and external stimulation. In environments where external variation is limited, emotional patterns may become more internally driven. This does not indicate instability but reflects adaptation to reduced environmental variability. Group dynamics within isolated crews or populations become especially important. In confined environments, social interaction is both essential and continuous. Small interpersonal changes can have amplified effects due to the lack of alternative social networks. Over long durations, maintaining stable group function requires careful attention to communication, shared responsibilities, and conflict resolution. Sleep patterns may also adjust in response to artificial lighting and structured schedules. Without natural day-night cycles, sleep must be regulated through controlled environmental cues. Consistency becomes important in maintaining circadian rhythm stability, which influences cognitive performance and physical health. Disruption in these patterns can accumulate over time, affecting overall functioning. Stress in isolated environments arises not only from external hazards, but also from the persistence of confinement. The absence of environmental change can lead to a form of psychological pressure that builds gradually. This pressure is not tied to a single event, but to the continuity of the same conditions over long durations. Management of this stress requires both environmental design and behavioral adaptation. The relationship between perception and environment becomes increasingly intertwined. The mind does not operate independently of surroundings, but continuously interprets and adjusts to them. In isolated conditions, this relationship becomes more uniform, with fewer external disruptions to reset or recalibrate perception. Over time, this can lead to a stable but narrow experiential range. In the broader context of interstellar travel, psychological isolation represents a non-physical constraint that interacts with all other limitations. Even if physical systems such as propulsion energy and life support are sufficient, the sustained experience of separation introduces a continuous cognitive and emotional demand. This demand accumulates over time rather than appearing suddenly, making it a slow but persistent factor in long-duration travel. The human mind remains adaptable, capable of functioning under a wide range of conditions, yet it does so within limits shaped by environmental structure. In extended isolation, those limits are tested not by abrupt changes, but by the long persistence of the same conditions. This creates a form of constraint that is temporal rather than spatial, defined by duration rather than distance. Propellant efficiency defines one of the most fundamental constraints on motion through space. In this region of travel mechanics, propulsion is not determined only by how much energy can be generated, but by how effectively that energy can be converted into directed motion. The governing relationship between mass velocity and fuel consumption introduces a structural limitation that shapes all rocket-based systems regardless of scale or technological advancement. At the core of this limitation is the principle that a spacecraft must carry the fuel it uses to accelerate, which means that every unit of added velocity requires not only energy, but additional mass to store and expel that energy. As fuel is consumed, the mass of the spacecraft decreases, which temporarily improves efficiency. However, the initial requirement to carry all necessary fuel from the beginning creates a compounding burden. This relationship causes the system to scale non-linearly, where increases in desired velocity demand disproportionately large increases in initial mass. In chemical propulsion systems, this constraint is particularly severe because exhaust velocity is limited by chemical energy stored in molecular bonds. The effectiveness of a propulsion system depends strongly on how fast reaction mass can be expelled. If exhaust velocity is low relative to desired spacecraft velocity, efficiency drops rapidly. This means that even large quantities of fuel produce diminishing returns in terms of achievable speed. As velocity requirements increase, the proportion of total spacecraft mass dedicated to propellant grows rapidly. Structural components, payload, and life support systems become a shrinking fraction of total launch mass. Beyond a certain point, nearly all carried mass would need to be fuel, leaving little or no capacity for functional systems. This creates a practical boundary where increasing fuel no longer results in viable spacecraft design. Staging systems attempt to address this limitation by discarding empty fuel tanks and engines during flight. This reduces mass and improves efficiency at different phases of acceleration. However, staging introduces mechanical complexity and cannot eliminate the underlying exponential relationship between velocity change and fuel mass. Each stage still obeys the same physical constraints, meaning that overall system scalability remains fundamentally limited. In higher efficiency propulsion concepts such as nuclear fission or fusion-based systems, exhaust velocities are significantly improved compared with chemical systems. This increases performance and reduces the fuel burden for a given velocity change. However, even these systems are still bound by the same exponential relationship between required velocity change and fuel mass. Improvements in energy density reduce the severity of the limitation but do not remove it. The mathematical structure governing rocket motion shows that each incremental increase in velocity requires exponentially more propellant when exhaust velocity is fixed. This means that doubling desired velocity does not simply double fuel requirements, it increases them by a much larger factor. As a result, attempting to approach relativistic speeds using onboard reaction mass becomes increasingly impractical. Another constraint arises from the storage of propellant itself. Large quantities of fuel must be contained within structural tanks, capable of withstanding pressure, temperature changes, and mechanical stress. As fuel mass increases, so does structural load, requiring stronger and heavier containment systems. This additional structural mass further increases fuel requirements, creating a feedback loop that amplifies inefficiency. Energy delivery to propulsion system must also remain stable over time. Long-duration burns require consistent thrust output, which depends on precise control of reaction processes. Instabilities in combustion or reaction rates can lead to inefficiencies or structural failure. Maintaining stability becomes more difficult as system scale increases, particularly when dealing with high-energy reactions. In space environments, the absence of atmospheric resistance means that velocity can be maintained once achieved, but it does not reduce the energy required to reach that velocity. Acceleration must still be achieved entirely through onboard energy reserves. Once propellant is exhausted, no further acceleration is possible, and motion continues only through inertia. This transition from powered motion to coasting defines the final state of propulsion-limited travel. As mission requirements extend toward interstellar distances, the amount of propellant required to achieve even modest fractions of light speed becomes extremely large. The energy cost of carrying that propellant increases total system mass to levels that quickly exceed practical engineering limits. Even with highly efficient propulsion, the exponential nature of fuel scaling remains dominant. This limitation is not dependent on technological maturity, but on the structure of momentum exchange itself. Every propulsion system that relies on reaction mass must obey the same conservation laws. This ensures that improvements in engineering can improve efficiency, but cannot remove the underlying scaling relationship. In this region of analysis, propellant efficiency becomes not just an engineering challenge, but a defining boundary on achievable motion. It governs how fast a spacecraft can accelerate, how long acceleration can be sustained, and ultimately whether interstellar travel can be achieved within realistic resource constraints. Within the broader framework of interstellar limitations, fuel scaling interacts with energy requirements, relativistic effects, and material constraints. Together, these factors reinforce a consistent boundary where increasing performance demands rapidly escalate system complexity and resource consumption. Propellant efficiency therefore represents one of the earliest and most persistent barriers to deep space travel. Engineering systems in space operate under conditions where repair opportunities are limited, environmental stress is continuous, and operational timelines extend far beyond typical terrestrial expectations. In this region of extended mission duration, failure is not a single event, but a probabilistic accumulation of small uncertainties. Every component, regardless of quality or redundancy, carries a non-zero chance of malfunction. Over short periods, these probabilities remain negligible, but across long durations they begin to compound into meaningful risk. Each subsystem within a spacecraft depends on the reliable performance of many smaller components. Sensors, processors, valves, structural joints, and electrical connections all contribute to overall system function. Even when individual reliability is high, the total number of components ensures that some level of failure probability always exists. As system complexity increases, the number of potential failure points increases as well, creating a larger surface for uncertainty. In short-duration missions, redundancy and testing can effectively mitigate these risks. Systems are designed with backup pathways so that a single failure does not lead to mission loss. However, redundancy itself introduces additional components, each with its own probability of failure. This creates a layered structure where safety improves locally but system complexity increases globally. Over long durations, small degradation processes begin to accumulate. Materials fatigue slowly under repeated stress cycles, electronic components experience gradual radiation exposure, and mechanical parts undergo wear even in low-friction environments. These processes do not cause immediate failure but gradually reduce performance margins. Systems that once operated with wide safety buffers may eventually operate closer to their functional limits. Radiation in space plays a particularly important role in long-term reliability. High-energy particles can alter semiconductor behavior, induce bit flips in memory systems, and degrade electronic performance over time. While shielding and error correction systems can reduce these effects, they cannot eliminate them entirely. As mission duration increases, cumulative exposure raises the likelihood of transient or permanent faults. Thermal cycling also contributes to long-term uncertainty. Repeated transitions between sunlight and shadow cause expansion and contraction in materials stressing joints and interfaces. Over time, these cycles can weaken structural bonds or alter alignment in precision systems. Even small shifts in alignment can have significant effects on instruments and navigation systems that rely on high accuracy. Software systems introduce another layer of complexity. Autonomous systems must operate without immediate human intervention, relying on algorithms to interpret sensor data and make decisions. While software does not degrade physically, it operates within hardware environments that do. Radiation-induced errors, memory corruption, or sensor drift can lead to unexpected system behavior, requiring robust error handling mechanisms. As mission duration increases, the interaction between hardware and software becomes more critical. Small sensor errors can propagate through control systems, leading to corrective actions that may not perfectly match actual conditions. Over time, these feedback loops introduce uncertainty into system behavior, requiring increasingly sophisticated fault detection and correction strategies. Human oversight can reduce some of this uncertainty, but communication delays limit the ability to respond in real time. When signals take years to travel between spacecraft and Earth, corrective instructions cannot be applied immediately. This forces spacecraft to rely heavily on onboard autonomy, increasing dependence on systems that must function without external validation. Manufacturing tolerances also play a role in long-term reliability. Even highly precise engineering cannot eliminate microscopic imperfections in materials and assemblies. These imperfections may not affect initial performance, but under sustained stress they can become points of weakness. Over long durations, these small variations contribute to divergence in system behavior. This statistical nature of failure becomes more significant as mission scale increases. Instead of predictable performance curves, long-duration systems operate under distributions of possible outcomes. Some components may last far beyond expected lifetimes, while others may fail earlier than anticipated. This variability makes long-term planning inherently uncertain. Environmental exposure adds further variability. Micrometeoroid impacts, radiation fluctuations, and temperature extremes introduce random external stresses that cannot be fully predicted or controlled. Even rare events become significant when exposure time is extended across decades or centuries. In this region of analysis, reliability is not absolute but probabilistic. Systems are designed not to eliminate failure, but to reduce its likelihood to acceptable levels. However, as mission duration increases, the accumulation of small probabilities becomes increasingly important. A system that is highly reliable over short durations may still face significant risk over interstellar timescales. The concept of engineering certainty therefore changes with scale. Short-term missions can be designed with high confidence in performance, but long-term interstellar missions must account for gradual erosion of that confidence. The longer the system operates, the more it transitions from deterministic behavior to probabilistic behavior, Within the broader framework of interstellar travel limitations, engineering failure probability acts as a quiet but persistent constraint. It does not impose a single barrier, but instead shapes the long-term viability of all systems. Even if propulsion energy and life support are sufficient, the accumulation of small uncertainties over time creates a growing envelope of risk. This makes reliability not just a technical requirement, but a defining condition of long-duration space systems. In environments where repair is limited and delay is unavoidable, even rare failures become structurally significant. Over interstellar timescales, the probability of at least one critical failure approaches inevitability, unless systems are fundamentally redefined. In long-duration space travel, the concept of returning to the origin point introduces constraints that are structurally different from those governing outward motion. While leaving a planetary system already requires overcoming gravity, and accelerating into interstellar space returning requires not only reversing that trajectory, but also carrying the necessary resources, timing, and control systems to execute a complex deceleration and reacceleration process. This asymmetry between departure and return becomes more pronounced as distance increases. A return journey requires that a spacecraft either carry additional propellant for deceleration or rely on external mechanisms to slow down upon arrival at a distant destination. Carrying extra propellant increases the initial mass, which in turn increases the energy required for launch and acceleration. This creates a compounding burden where the requirement for return capability significantly increases the difficulty of the outbound journey itself. At interstellar distances, the challenge becomes more severe. A spacecraft traveling to another star system must not only accelerate to high velocity, but also decelerate upon arrival to avoid passing through the destination without meaningful interaction. Without deceleration, the spacecraft would continue through the system at high speed, limiting its ability to study, explore, or interact with local environments. However, deceleration requires either propulsion in reverse or interaction with external fields, both of which demand additional energy or infrastructure. External deceleration methods such as gravitational assists or magnetic braking depend on specific environmental conditions that may not be present or sufficiently strong in all target systems. Gravitational braking requires precise trajectories through dense stellar or planetary regions, which may not align with safe or practical navigation paths. Magnetic or plasma-based braking depends on environmental structures that vary significantly between systems. This variability makes reliance on external deceleration uncertain. If onboard propulsion is used for deceleration, the spacecraft must carry enough fuel for both acceleration and deceleration phases. This effectively doubles the energy requirements compared to a one-way journey, because fuel mass scales exponentially with velocity change. This doubling effect is not linear but dramatically increases total system mass and complexity. Time delay further complicates return feasibility. Communication between origin and destination becomes increasingly delayed as distance increases, making coordination for return timing difficult. Any changes in mission objectives or environmental conditions cannot be quickly communicated or adjusted. This lack of synchronization introduces uncertainty into return planning, especially for missions that rely on precise timing windows. In some scenarios, orbital mechanics may allow partial energy recovery through gravitational interactions. A spacecraft can use the gravity of stars or planets to adjust its trajectory and reduce fuel consumption. However, these maneuvers require precise alignment and timing, which may not be achievable in all interstellar contexts. Additionally, gravitational assists primarily redistribute energy, rather than eliminate the need for initial high-energy input. The structural asymmetry between outbound and return trajectories becomes more pronounced as velocity increases. At low speeds, returning is relatively straightforward because energy differences are manageable. At relativistic speeds, however, even small deviations in velocity translate into enormous energy requirements for correction. This makes return trajectories increasingly sensitive to initial conditions and external perturbations. Life support requirements also differ between outbound and return phases. A return journey must account for extended duration potential delays and system degradation over time. Any failure in life support during the return phase cannot be quickly corrected due to communication delays and distance. This increases the need for redundancy and further increases system mass, reinforcing the same scaling constraints seen in propulsion systems. Psychological and operational factors also influence return feasibility. The expectation of return introduces planning constraints that affect mission design from the outset. Knowing that a return is required limits acceptable risk levels and increases system redundancy requirements. These design choices increase complexity and reduce overall efficiency of the mission. In many theoretical mission designs, the return phase is often the most resource-intensive part of the journey. This is because it must account for worst-case scenarios, including system degradation, after long exposure to interstellar conditions. As a result, return capability often dictates the overall feasibility of a mission more strongly than the outbound journey itself. At extreme distances, return may become effectively impractical, even if outward travel remains theoretically possible. This is because the energy, time, and resource requirements for reversing the journey exceed available system capacity. In such cases, missions become inherently one-way not due to technological limitation alone, but due to the cumulative constraints of physics, energy, and distance. This asymmetry defines a fundamental characteristic of interstellar travel. Outward motion expands possibility while return contracts it. The farther a system travels, the more the return path diverges from practical feasibility. This divergence grows with distance, energy cost, and time eventually reaching a point where return is no longer a symmetric counterpart to departure, but a separate and far more demanding problem. Within the broader framework of interstellar limitations, return feasibility acts as a structural boundary on mission design. It influences propulsion requirements, energy budgets, life support systems, and psychological expectations. Even if all other constraints are addressed, the difficulty of returning reinforces the overall challenge of sustained interstellar travel. The final constraint emerges when all previous layers of limitation are considered together within a single, continuous framework of motion, time, and existence. In this region of synthesis, interstellar travel is no longer evaluated as a sequence of isolated problems, but as a unified system in which distance, energy, biology, communication, and reliability interact simultaneously. Each constraint reinforces the others, producing a combined structure that is more restrictive than any individual factor alone. Human lifespan forms one of the most immediate temporal boundaries in this system. Biological time is measured in decades rather than centuries, and even under optimal conditions, the duration of a human life remains finite and relatively short compared with interstellar distances. Even journeys to the nearest star systems require time spans that extend beyond typical lifetimes when constrained by realistic propulsion and energy limits. This creates a separation between biological existence and cosmic scale that cannot be easily reconciled. Time dilation at high velocities introduces a partial modification to this relationship, but it does not remove the underlying constraint. While relativistic effect can alter the passage of time between reference frames, the energy required to reach such velocities remains prohibitive. As a result, the theoretical possibility of time adjustment does not translate into practical travel capability under known physical conditions. Generational continuity becomes a conceptual response to this limitation. Instead of a single traveller completing a journey, multiple generations would need to maintain continuity over extended periods. This introduces additional constraints related to social structure, resource management, and system stability over centuries. However, even generational systems remain subject to cumulative risks from radiation, material degradation, system failure, and psychological drift, all of which increase with time. Cosmic timescales further emphasize the mismatch between human experience and interstellar distances. Stars evolve over millions to billions of years, and galactic structures persist across even longer intervals. Within this context, a single interstellar journey occupies an extremely narrow slice of cosmic time, yet remains vastly longer than human-scale planning horizons. This disparity highlights the difficulty of aligning biological, technological, and cosmic timeframes into a coherent operational model. Energy constraints continue to reinforce this limitation even at the highest theoretical levels of propulsion. As velocity approaches relativistic regimes, energy requirements increase to such an extent that they dominate all other considerations. Even if advanced energy sources are assumed, the exponential relationship between velocity and energy ensures that only a limited range of travel speeds remains practically accessible. This restriction defines a persistent boundary on achievable transit times. Material and system degradation accumulate across the entire duration of travel. Over long periods, even small probabilities of failure become significant. No system remains perfectly stable indefinitely, and the longer the duration, the greater the likelihood that some component will deviate from expected performance. This cumulative uncertainty introduces a growing divergence between planned trajectories and actual outcomes. Communication delay reinforces the sense of separation between origin and destination. As distance increases, information exchange becomes increasingly asynchronous, eventually losing real-time coherence entirely. This disconnect affects not only operational control, but also the continuity of experience between observers at different locations. The further the journey extends, the more fragmented the informational link becomes. Psychological adaptation also evolves over extended durations. The human mind, while capable of adjusting to stable environments, does so within limits defined by sensory variation, social interaction, and temporal reference points. In prolonged isolation, these reference structures become increasingly distant or abstract, altering perception of time and connection. This change is gradual but persistent, reflecting the cumulative nature of environmental adaptation. When all constraints are considered together, a consistent pattern emerges. Each system involved in interstellar travel operates under a scaling law that becomes more restrictive as distance and time increase. Propulsion requires more energy. Energy systems require more infrastructure. Life support requires more stability, and reliability requires more redundancy. Each improvement in one area increases demands in another, producing a tightly coupled system of interdependent limitations. This interdependence creates a condition where interstellar travel is not prevented by a single barrier, but by the combined effect of many reinforcing constraints. The structure of space-time, the properties of energy, the behavior of matter, and the nature of biological systems all contribute simultaneously to this outcome. No single modification appears sufficient to remove the full set of limitations without introducing new ones elsewhere in the system. The universe itself does not prohibit motion between stars, but it defines strict conditions under which such motion must occur. These conditions include finite speed limits, energy scaling laws, material degradation processes, and temporal mismatches between systems of different scales. Together they form a consistent framework that governs all attempts at large-scale traversal. In this final synthesis, the reason humanity will never travel easily between the stars is not attributed to a single impossibility, but to the convergence of multiple physical realities. Each layer of constraint builds upon the others, creating a landscape in which interstellar travel remains theoretically describable, but practically unattainable within known physical and biological limits. The system closes not with a single barrier, but with a network of interlocking boundaries that reinforce one another across distance and time. Within this structure, motion remains possible, but the conditions required for sustained practical and return-capable interstellar travel exceed the combined capacities of current and foreseeable systems.